So, we said a next word predictor becomes powerful when it deeply understands context, and earlier approaches could handle some context, but they struggled with the long-range kind. The architecture that cracked that problem, the one inside almost every modern LLM, whether it's ChatGPT, Claude, Gemini, or Llama, is called a transformer. It was invented by a team of researchers at Google in 2017, and it is, without exaggeration, one of the most important inventions of the last decade. What makes the transformer different is that it lets every word look directly at every other word, no matter how far apart they are. It builds a rich, deep understanding of what every word means in relation to every other word. That understanding is what turns next word prediction from a neat trick into something that feels like intelligence. We won't be going through every detail, that would take hours. But here, we want to walk through the big ideas, because once you see how this context engine works, a lot of things about AI suddenly make much more sense. There are 4 key steps in the working of a transformer: embedding, attention, the feed-forward layers, and unembedding. Let's take them one at a time. First, embeddings, giving words meaning through numbers. Remember, the model only works with numbers. So the very first thing it has to do is take each token and convert it into a list of numbers that represents the meaning of that word. This list of numbers is called an embedding, or, if you want the technical term, a vector. So the word king might become a list of, say, 12,000 numbers, and queen becomes a different list of 12,000 numbers, and banana becomes yet another list. Now here's the beautiful part, these lists aren't random. During training, the model learns to place words with similar meanings close together in this number space, and words with different meanings far apart. King and queen end up with very similar lists of numbers because they appear in similar contexts, they share a lot of meaning. King and banana, very different lists, far apart. And it goes even deeper than that. You can actually do arithmetic with these vectors. There's a famous example. Take the numbers for king, subtract the numbers for man, add the numbers for woman, and what you get lands right next to queen. The model has somehow encoded the concept of gender as a direction in this number space. Nobody programmed that in. It figured it out on its own just by trying to predict the next word. So now every token has been converted into a rich list of numbers, it's embedding, but at this point, each word's embedding only reflects what that word means in isolation. It doesn't know what sentence it's in. It doesn't know what words are around it, and that's a problem, because context is everything in language. That's where attention comes in. This is the big one. If there's one mechanism that makes transformers special, one idea that changed everything, it's attention. Here's the problem attention solves. Take the word bank. In one sentence, I sat by the riverbank. In another, I deposited money at the bank. Same word, completely different meaning. The embedding for bank starts out the same in both sentences, it's just the default meaning. But the model needs to figure out which meaning is right. And the only way to do that is to look at the other words in the sentence. That's what the attention mechanism does. It lets every word look at every other word in the text and ask, which of you are relevant to me? How should you change my meaning? In the first sentence, bank pays attention to river and updates its internal numbers to lean towards the riverbank meaning. In the second sentence, bank pays attention to money and deposited and shifts towards the financial institution meaning. After the attention step, bank is no longer just a generic word, it's been contextualized. Its list of numbers has been updated to reflect not just what bank means in general, but what it means right here in this specific sentence. And this doesn't just happen for bank, it happens for every token simultaneously. Every word reaches out to every other word, gathers relevant information, and updates itself. It's a massive parallel exchange of information. Here's an example that makes it vivid. Imagine you're reading a murder mystery and the very last sentence of the book is, "The murderer was blank." To predict that final word, the model can't just look at the words "the murderer was." That's not enough. It needs to have absorbed the entire novel, every clue, every alibi, every suspicious glance, and funneled all of that information into the representation of that final blank. That's what attention does. It's the mechanism by which information travels across the text. It's how a clue mentioned on page 3 can influence a prediction on page 300. Without attention, the model would be stuck looking at just its immediate neighbors. With attention, information can flow from anywhere in the context to anywhere else. Okay, so after the attention step, every token has been updated with context from the words around it. But the processing isn't done yet. The updated embeddings now pass through what's called a feed-forward network or sometimes an MLP layer. Here's a simple way to think about what these layers do. If attention is about gathering context, what other words are relevant to me? Then the feed-forward layers are about reasoning with that context. Now that I know what's around me, what does that mean? Think of it like a question and answer session. After the attention updates the word bank with the context that river is nearby, the feed-forward layer asks a series of questions about that updated meaning. Is this referring to a natural feature? Yes. Is this likely to be followed by words about water, nature, or geography? Probably. Should I increase the probability of words like flowing or muddy as the next word? Yes. None of these questions are literally written out, of course. It's all happening through matrix multiplications and mathematical operations. But the effect is that these layers refine and enrich the model's understanding of each word using the context that attention just gathered. And this is also where a lot of the model's factual knowledge lives. Remember the lossy zip file from earlier? The patterns, the facts, the associations, a huge portion of that compressed knowledge is stored in the parameters of these feed-forward layers. Now here's what ties it all together. The model doesn't do attention and feed-forward just once. It does them over and over, in a stack. A typical large model has around 80 to 100 of these layers. Each layer runs attention. Words talk to each other, then feed forward, each word refines its meaning. Then the output gets passed to the next layer, which does it all over again. Early layers tend to pick up basic things: grammar, syntax, simple word relationships. Middle layers start to build more complex understanding, sentence, meaning, tone, topic. And the deepest layers handle the most abstract stuff: reasoning, implied meaning, things that require putting many pieces together. By the time data has flowed through all 100 or so layers, that initial embedding, that simple list of numbers for each word, has been transformed into something incredibly rich and contextual. Now I want to share something that I think is really useful for how you use these models day to day. There's a fixed amount of computation the model can do per token. Every token that passes through the model goes through the same pipeline: embed, attention, feed forward, repeat across 100 layers. That's it. That's all the thinking the model gets to do for that token. So, what happens when you ask the model a hard question and demand a one-word answer? It gets one token's worth of thinking, one pass through the pipeline. That's all. But what if you let the model reason step by step? What if you say, think through this carefully? Now it's generating many tokens, and each one is another pass through the full pipeline. Each token is more computation, more time to think. Think of it this way. If you ask, what is 347 times 28, answer in one word, the model gets one shot, and it might get it wrong. But if you ask it to show it's working step by step, it generates dozens of tokens of working out, each one a full pass through the network. This is why models perform dramatically better when you let them think out loud. It's not being verbose for fun, it's not wasting your time. Each token is genuinely more computation. More tokens literally equals more thinking. This is also why the latest models, the ones that show a thinking phase before answering, perform so much better on hard problems. They're giving themselves more tokens, which means more passes through the pipeline, which means more computation. Alright, so the text has flowed through all the layers. Every token's embedding has been refined and enriched through dozens of rounds of attention and feed forward. Now we're at the very end of the pipeline. The model looks at the final token's embedding, this rich contextualized list of numbers, and it needs to convert that back into a prediction, back into words. It does this through something called unembedding. It takes that final vector and transforms it into a probability distribution, a score for every single word in its vocabulary. Something like this. And then it picks one. Usually, but not always, the one with the highest probability. There's a bit of randomness thrown in, which is why you can ask the same question twice and get a slightly different answer. That randomness is actually a feature. It makes the model more creative and less robotic. And that's it. That's one token generated, one word. And to generate the next word, you take the entire sequence, including the word you just generated, feed it all back through the whole pipeline and do it again, and again, and again, until the response is complete. So let's zoom out. Here's the full journey of a single prediction. Text comes in, it gets broken into tokens. Each token gets an embedding, a list of numbers representing its meaning. Attention lets every word gather context from every other word. Feed-forward layers refine that understanding. This repeats across 100 or so layers. The final embedding gets unembedded into a probability distribution. The model picks a word and then it repeats for the next word. That's a transformer. That's what's running inside every time you send a message to ChatGPT or Claude. But here's the thing, after all of this training, after processing trillions of tokens and tuning billions of dials across this incredible architecture, what you end up with is not a chatbot, it's not an assistant, it's a text prediction engine. You give it a piece of text and it continues it the way the internet would. To turn that raw prediction engine into the polished, helpful assistant you actually talk to every day, that takes one more step, and that's what we'll cover next.